uh, when you're talking about Legionella and Chlamydia being they need intracellular parasites, right? That they need to be inside the cell. But for the likes of Chlamydia, those are just specific bacteria. But when we're talking about viruses, all this is virus to be infectious to put inside itself. And the constitution of a virus is very simple, basic. No, the right word is two basic components. Number one is a capsid. This capsid you can think of it as a wall, right? And a nucleic material. The nucleic material can be either DNA or RNA. Remember, it's DNA or RNA. It can't be both. It's DNA or RNA. That's why we'll say we have DNA viruses. We'll say we have RNA viruses, right? But there's no such thing as a virus containing both the DNA and the RNA. Yeah. So basically, and okay, that's why we call a virus can also, we just refer to it as a nucleocapsid, right? Rather, that term coin, is it here? Nucleocapsid, where it's the nucleic material here and the capsid. You know, those are the two basic components of a virus. The genetic material and the capsid. The genetic material and the capsid. And now for other viruses, we'll see that they do have an envelope, something that protects it further, that they have an envelope. But funny thing is that, for example, COVID-19 is an envelope virus. It contains an envelope, right? But it is more susceptible to these antiseptic measures, such that if we just destroy the envelope, then the virus will also be destroyed. So the envelope is an extra layer of protection, but it's like the virus now depends entirely on the envelope. So once you attack the envelope, once you damage the envelope, this virus is as good as dead. And that is why sanitizing worked for COVID, right? Because that sanitizer was just disrupting this envelope. Once you've disrupted that envelope, then you've killed COVID-19. Okay. And then so viruses, they are, once they get inside the cell, what they do is just they hijack your cell. Within a virus on its own, it does not have the capability to make the proteins. It does not have the capability to replicate, right? But so that is why a virus desires to be inside your cell, because once it's inside your cell, the virus can now replicate. It can use your ribosomes to make its own proteins, right? In short, once a virus enters your cell, it hijacks your protein synthesis machinery. It even hijacks your replication machinery. The virus will come with some of its enzymes, but it will hijack your cell to make its own stuff. So essentially what was happening with COVID is you inhale just one, like for example, one virion of COVID gets inside your cell, replicates, and then that cell produces like 50 more COVIDs that infect 50 other cells. You see? That's why the name viruses, they are dangerous stuff. But funny thing, they are the smallest. They are the tiniest, right? we measure viruses in terms of nanometers. With bacteria, in terms of micrometers. But here it's nanometers. It's among the tiniest stuff. So regarding the general characteristics, we will see that they'll be divided, number one, into DNA viruses and RNA viruses. Remember we said it can contain both DNA and RNA. So they'll be divided into DNA viruses and RNA viruses. That will be, that's one classification. The other classification, we can also divide them based on enveloped viruses and non-enveloped viruses. Enveloped viruses and non-enveloped viruses. Remember, we've said the enveloped viruses, they are more sensitive to these antiseptic techniques as compared to the non-enveloped viruses. Then, clinically, now, when it comes to the clinical aspect of this virology, we'll mostly look at them in terms of the disease they cause, right? Like herpes simplex causes herpes, chicken pox is caused by varicella zoster, hepatitis, HIV, you know, these are the common viruses. The likes of polio, the likes of the measles, you know, these viruses. That is how we'll be looking at them. But so looking at the genome, we said it can be either RNA or DNA. Now, the RNA can be either single-stranded or double-stranded, and so can the DNA. But generally, the RNA is usually single-stranded, and the DNA is usually double-stranded, typically. Then, when we, just to take you back, when we were saying this one has RNA, we used to put a sign, positive and negative, just down here. RNA viruses and stranded RNA viruses. So that positive stranded RNA viruses, it simply means that a positive stranded RNA via our ribosomes to make proteins directly without any modifications, any changes, any transcription, right? But when we say a negative stranded RNA virus, it means that RNA that is its genome, it cannot be directly translated by our ribosomes to make proteins. It has to be converted to a positive stranded RNA, or rather, it has to be converted to a messenger RNA, which can be translated to make protein. In short, a positive stranded RNA is equal to a messenger RNA that can be directly translated to make proteins. A negative stranded RNA, we have to synthesize an messenger RNA to make proteins. The capsid won't dwell much here on the capsid, the symmetry, but it is, I hope you've understood now, because that's the basics of viruses, that they contain a nucleic acid surrounded by a capsid. Nucleic acid surrounded by a capsid. Some have envelopes, some do not. Now, let us look briefly at replication, or rather, how does number one, how does a virus behave? If I can remember, when we covered bacteria, we said there's a lag phase, there's a log phase, stationary phase, and death phase. That's what we said when we were covering bacteria: lag, log, stationary, then death. Lag, we said the bacteria is a balance. Death, toxins have accumulated, competing for space, so viruses are dying, resources are finished. Bacteria are dying because the resources are finished. So that was the growth of bacteria. Lag, log, stationary, then death. The log phase, we also call it the exponential phase. Now for viruses, you can already see the graph, right? It's a U. You can say it's a U. For our, you can say it's a U, like if you are to just casually draw this, right? This is a U. This is a U, right? And this is called the one-step growth curve of a single cell infected with a single virus particle. Now, let's look at this. I'll be going back to COVID-19 because COVID-19 is likely to be tested because it's a virus and it's the most recent thing that has happened to us since recently. So, a virus, we've said number one, it's an obligate intracellular organism. Obligate, we said obligate, it means do or die, right? Do or die. Meaning if it doesn't enter the cell, the viruses perish, right? It's an obligate intracellular organism. Remember, we even saw with obligate and facultative when we're looking at metabolism, right? Like so, facultative anaerobic metabolism, which we majorly saw in the gram-negative rods that we were looking at yesterday, the likes of E. coli, Salmonella, and all those stuff, right? Now here we said viruses are obligate intracellular. They have to get inside the cell. If they don't, they die. So this graph, it represents, now I want to picture one virus, or rather one, let me even call it one viral cell. No, one virus particle or one virion, right? This is how it will be represented. And we will explain why the virus at some point we will not be able to see it, and then we are able to see it. Though it's what you expect. It's what we've said, that the viruses enters the cell, hijacks your protein synthesis, make it hijacks your synthesis of proteins, hijacks your DNA replication, or your replication machinery to make its own. Right. Okay. Now let's start here with the eclipse period. Eclipse period. Remember now for this, we live in, I want us to work with this graph here so that you can see that we are working with a single virus particle. Now in the eclipse period, I'm in a room somewhere, someone has coughed, a single COVID-19 particle of COVID, I've inhaled it, right? I've inhaled that single particle. So once I've inhaled it, it goes to my respiratory cells, right? It attaches to one cell. It attaches to one cell. And that will mean that once it has attached to one of my respiratory cells, that specific particle, remember, we are looking at it as one. I'm assuming just one entered. So that specific virus particle, it can't infect any other cell at that time, right? Because it has attached to that one cell. It's like it has committed that this is the cell we are taking, right? And now this is the eclipse period, whereby it's this time between when that virus enters my cell, it releases its nucleic acid. Now, in our case, in COVID-19, it releases that DNA, not DNA, that RNA. That RNA is picked up by my ribosomes to start making its own protein. But this process takes time. It's not as if it enters, the RNA is released immediately, and it's already making proteins, right? It's not a simultaneous thing at the and attachment entry, and it has already hijacked your stuff. It takes time, and that's why we are seeing here we were able to see one virus attached to my cell. We tracked it. And then it released its RNA. It released its RNA into my cell. And now, essentially, that virus has disappeared. What we just have is a copy of its RNA, right? And that's why it's 0, because at that point, we have if we can visualize my cell at that particular point, I don't have a virus particle inside my cell. What I have is what? Just some foreign nucleic acid, just some foreign some foreign RNA in the case of COVID. That's all I have, right? And during this time, what is happening is that the RNA, through the various mechanisms, that COVID-19 hijacks my replication, hijacks how I synthesize my DNA, or now for COVID specifically, it hijacks my ribosome. Starts making its own proteins. One of those proteins replicates that COVID RNA, right? So it starts making more copies of itself. But remember, something unique is happening. It's that the virus, yes, it's making its proteins. Yes, it's making its various enzymes. It's making all that it needs. However, all that it is actually making, its ingredients, right? For example, let's say it's you, a human, right? A human and your DNA. Let's picture it that way. And that you hijack a room. So you've entered you've entered into I want to make it relatable. Let's say it's LT4, right? That you want to hijack LT4. So you go, you reach the door. Once you reach the door, because you can't enter in your form as a human, you release part of you, right? Let's say in this case, it's your hand. You cut off your hand and you throw it inside LT4. So at that moment in time, in LT4, we will say there are 0 humans inside LT4. There's a hand, yes, but that's not a human. That's just a hand. So we'll say that at that moment in time, the number of humans in LT4 is exactly 0. But then your hand is able to do what? It's able to make you somehow, now this beginning in this story, somehow imagine your hand is able to make your liver, it's able to make your kidneys, it's able to make your eyes, but it's making them individually. Let's go, for example, let's say it's going to the first desk and it's making a liver. It goes to the second desk, it mixes ingredients 1 and 2 and makes a kidney there. It goes to desk number 8, it makes an eye for you, it makes a nose for you. Eventually, it makes all the parts of you that make you human. So still, without us assembling those parts, still we will say in LT4, there are no humans. Yes, there's a liver somewhere, there's a kidney chini ya desk, there's an eye at the whiteboard, there's a hand somewhere there, but there is no human in LT4. However, now, imagine now that your hand is able to bring together all of these parts of you now to make a full human, right? It's able to bring your liver, connects it to your intestines, connects it to your everything. In short, we make a human being from the parts that the hand has specifically synthesized while inside LT4. Now, at that point, once we've accumulated all the parts that a human being needs, we will say higher. LT4 actually has now one human, right? We'll say now LT4 has one human. And that is what explains this U. The virus was there, it was detectable, it entered your cell, it disappeared, it released its RNA. Let's say for COVID, let's work with COVID. It released its RNA inside this cell. The RNA went to the ribosome, started making the COVID-19 proteins, started making the enzyme that COVID-19 needs. And this process happened for these 10, 12 hours, right? But at no point did these specific individual parts, the enzyme, the RNA, they didn't come together. But at the 12th hour, the 13th hour, the 14th hour, they came together to make one virion, right? To make that, in short, to resynthesize that one single particular viral cell. And that's why here the concentration now goes back to 1. Or rather, not the concentration, the number of viruses in my cell goes back to 1. But we know it's not as if the virus goes that slowly, like it won't synthesize at we've made one RNA, we've made one RNA polymerase. Now let us assemble it together, then say, yeah, we've made one virion. Now let us start in the beginning again. No, during this eclipse period, the virus has seen through my ribosomes, it has synthesized 100 copies of its RNA. It has synthesized 100 copies of its specific enzymes. And that's why after this time, the concentration shoots, or rather the number of viruses in my cell shoots, after which they will be released. They'll be released and they'll go to infect other cells. So that is simply the explanation of this one-step growth curve, that it's a U. First of all, the concentration goes down to 0. Here, the virus is making its own stuff. Then it peaks again because now the virus has come together. The hand, the liver, the kidney, they've come together to make one human. Yeah. So I hope we've understood that, why it's a U-shaped thing. Now let us look at the steps in replication of virus. Though I've already just mentioned it in passing. So the first thing that a virus will do, or rather the first thing it needs to do, is attach to a specific receptor, to a specific site, right? For COVID-19, it needs to attach somewhere. We know for HIV, it targets CD4 specifically. We'll be looking at those CCR5, CXCR4, things like those, right? It needs to attach to a receptor, right? It doesn't just enter, it needs to attach to a receptor. So that tells us, number one, if we are looking to treat COVID, we can target the receptor it binds to before it enters into the cell, right? Like ideally, if COVID binds to a specific receptor before, and that receptor is what facilitates its entry inside the cell, then that means if we're able to block that binding to the receptor, then there's a possibility we will have prevented a person getting sick from COVID. And currently, okay, there's a drug that is an old drug that has been there for a while that has been shown to actually do this, specifically for COVID-19. It decreases the expression of S2 receptor, which is the receptor used. Yeah, anyway, that is just developing things. Anyway, so we say the first thing it needs to do is to attach. Once it attaches, now the next thing that it will do is it will be like absorbed, like it will be hugged, right? Here it is. The virus has bound to the receptor, or it has attached to the receptor. Then what will happen? it's like here it's hugged, or different different viruses work by different mechanisms. But here it has attached. After attaching, what the virus does is it penetrates into the cell. So the virus attached onto the receptor, then now it penetrated. Once it penetrates into the cell, what the virus now wants to do is to release its nucleic material. And how it do this? There is uncoating. Remember we said there are two basic components, the nucleic acid and the capsid. The nucleic acid, which is the RNA or DNA, it's found inside the what? It's found inside the capsid, right? So we need to uncoat, we need to release that nucleic acid, because that nucleic acid is what will hijack, that nucleic acid is what will essentially lead to that infection. So it releases that nucleic material. That nucleic material is now what will go ahead to remember, it's just not only nucleic material, it will also have some enzymes inside there, like the enzyme to replicate that nucleic material, or the enzyme to synthesize something that it needs. But essentially, it's the virus first, it attaches to the cell, or rather to the receptor. After attaching, it penetrates, right? After penetrating, it's now inside the cell, it releases, or rather it uncoats its stuff. Once it uncoats, it releases its genetic material. The genetic material will be taken up by the cell, by our host cell, now in this case, by my respiratory cells. Once it's taken up by my respiratory cell, it's done what? My respiratory cell, instead of making my own proteins, instead of making the proteins I need, it starts making the proteins of COVID-19, right? Then it's able to release. Then these proteins are able to accumulate, where once they are synthesized, they're able to accumulate somewhere. They are usually around the cell membrane. It's like the proteins agree to tapatana hapo. They meet there, and then the virus, either some viruses, they will lead to lysis of your cell. Some viruses will lead to, they will just leave your cell and go and infect other cells. So let me just display a diagram that summarizes this. Yeah, so you can see this is the general life cycle of a virus. Here it is. The virus, number one, it has attached. After attaching, it has entered, or it has penetrated inside the cell. Then you can see once it has penetrated, it has released its genetic material, the copies of the genome. So what will happen is that there'll be replication and gene expression of the gene we are expressing is now the viral genes. So what will we be making? We'll be making this viral proteins, right? Remember, here's the viral RNA in our host, in our ribosome. It makes these proteins. Then we've also replicated our nucleic acid. So the proteins and the nucleic acid, they come together, they make a new virion, a new virus particle. And that virus particle says, so this is what we said, assembly. It's like, iliambiana at 9 p.m. guys, tuna meet pale kwa wall, then tunatoka, right? Yeah, Indio, you can say this is the kennel before end of the show. They meet there, and then off to infect a new cell. So essentially, attachment, entry, uncoating, gene replication, and then assembly. First, they have to Remember what we said about the hand in LT4. The liver, the heart, whatever, all the organs, first of all, they have to come together. They have to assemble into now a human, so that they can now leave the cell as new virions, new viruses. And also this can help us explain why the Nini is a one-step growth curve. Remember here, when the virus attached, we're able to say that there's a virus there, right? But when the virus enters and releases this nucleic acid component, this RNA, this DNA, inside this cell, before assembly of the newly made virus particles, then the number of viral cells, the number of virus particles inside my cell is 0. Once they assemble is now when we say they are more than 1, or rather even more than 0. Yeah. So that's a step of how a virus infects you. Then briefly, we look at, remember the major classification of viruses is DNA viruses and RNA viruses. DNA viruses and RNA viruses, right? And we've mentioned that the central goal, the chief goal, the foundation goal of a virus is, number one, to enter into your cell and make copies of itself. Remember, copies of itself is its nucleic material, whether DNA, whether RNA. That's the number one goal, is to make copies of itself, right? And of its proteins, so that it can be whole again, and it can go infect other things. In short, its goal is to replicate. Its goal is to replicate. So, if its goal is to replicate, and we are saying there are DNA viruses and there are RNA viruses, and its goal is to replicate. In terms of replicating of the DNA, that one is, and also of the RNA, you can say that one is straightforward. You know, they've already said there's the likes of DNA polymerase, RNA polymerase. That one, let's even set that aside. In terms of replication, we look at it when we're talking about these viruses specifically. But let us talk about the proteins, right? The proteins. You know, at the very least, at least in our cells, in the host cell, to make a protein, you have to have a messenger RNA that goes to the ribosome so that it can be translated to make proteins, right? Central dogma of molecular biology. The information will flow from the DNA to the RNA to the protein, right? So it can't, at no point, we can't skip any of that. Information has to flow from DNA to RNA to proteins. So for RNA viruses, and we said for the positive stranded, you can say in brackets, or positive single-stranded RNA virus. We've said that RNA acts as a messenger RNA. That means when this virus gets inside your cell, making of its protein is PAP, right? Making of its protein is immediate. But for now let us look now for DNA viruses. DNA viruses, right? DNA viruses are things such as what? The Herpes viridae family. The Herpes viridae, we have the likes of herpes simplex, we have the likes of chickenpox, in EBV, Epstein-Barr virus, cytomegalovirus, right? Those are DNA viruses. Another famous DNA virus is hepatitis B. Hepatitis B is unique as being the only hepatitis that is a DNA virus. All the other hepatitis A, C, D, and D, they're all RNA viruses. But Hep B is a DNA virus. Hep B is a DNA virus. The other ones, they are RNA viruses. So, first, let us start by looking at this DNA virus. How does a DNA virus replicate? And more to the question, how will a DNA virus make its protein? And you said to make proteins, we need RNAs. We need RNAs. So I want you to imagine this is, I don't know, let's say Hep B, right? This is Hep B. Hep B, we've said, is a DNA virus. Hep B is a DNA virus. Don't forget that Hep B is a DNA virus. The other ones, Hep A, C, D, E, all the other ones are RNA viruses. So this is a Hep B virus. It has done what? Steps of infecting a cell. It attached to our liver cell, right? Once it attached, it's penetrated or it entered. Once it entered, it released its DNA material, right? Now we are at that point. Here is the hepatitis B DNA material. Now we want to know what happens next. At what point does this DNA virus starts making its own proteins? And what is the mechanism behind that that step? And it's all here. So here it is. Hep B has released its DNA. Remember we said they are in the nucleocapsid in the virus, that there are two key things, right? There's the capsid, right? The one surrounding it, and there's the nucleic material, either the RNA or the DNA. Now for Hep B specifically, we'll say there's the DNA and there's the capsid, right? Those are the two major. Those are the ones you won't miss in any virus. But viruses also carry their own enzymes. They carry their own enzymes. And when we say proteins, you know, I remember enzymes are proteins, right? Enzymes are proteins. So viruses, they carry their own proteins or their own enzymes. Let me call them enzymes so that it's easier to relate here. So this Hep B, it has come with its own enzyme. And which enzyme is this? An enzyme either that can synthesize its messenger RNA from its DNA, right? For some specific DNA viruses, we'll see they hijack our own mechanism. They use our own enzymes to make their RNA. But for others, they carry their own enzyme. Yeah, called DNA-dependent RNA polymerase. DNA-dependent meaning it acts on DNA. RNA polymerase meaning it makes RNA. So that DNA-dependent RNA polymerase, it makes these things we call early messenger RNAs. And we'll see why we call them early messenger RNAs. Those early messenger RNAs, will be translated and they will make early proteins. These proteins, why are they important? And why are we calling them early proteins? It's because now these proteins, they're the ones that come back to the DNA that was released and start replicating that DNA. They start replicating this DNA, right? And we're able to form now this daughter DNA or the new DNA. Then now, when it's like, I think we've synthesized enough copies of our DNA. So it's basically like, what else do we need? We're like, hey, we need some proteins, we need some enzymes. So now they transcribe the other part of their gene. They transcribe the part of their gene that would lead to replication of the DNA. Now they transcribe the other part. The other part is what will now produce these late messenger RNAs, which will produce late proteins. These late proteins are the ones which will be, which now the virus needs, now the Hep B needs, right? Once we synthesize our late proteins, now our virus is complete and it's able to go and infect other cells. So in short, for DNA viruses, it's what you'd expect. First of all, we'll convert that DNA to RNA. We'll translate the RNA to make the proteins. So at least you can memorize it as that we need to change our DNA to RNA to make our protein. Okay. Then let's looking at RNA virus. Usually the positive strand. The positive strand, that is very straightforward. You say the positive stranded, that one, the RNA serves as a messenger RNA, right? Goes directly to the ribosome. Ribosome, quick, it's able to make its proteins, right? Then, we want to look at the negative strand. The negative strand. Now, for the negative strand, in this case, we say just that the RNA cannot act directly as a messenger RNA. So what do we need? Remember, we already have RNA. So what do we need? We just convert it to a form that, or to a messenger RNA. Now, because the virus knows, hey, these humans can't convert this for us, the virus goes around carrying its own RNA-dependent RNA polymerase. So it's able to make its messenger RNA from this negative strand, and then where the virus is now able to make its own proteins. Those proteins, they will accumulate with the progeny nucleic acid that has been made, and we're able to synthesize what? We're able to synthesize a new virion particles. So unless someone has something to add in terms of replication, there's a lot also that is nini. There's a lot that, of course, we are leaving out, but that is essentially it. So if there's nothing, we can start at 8:25. We can start on what we have to cover next. Let me check what it was. Yeah. You can look at HIV virus. Yeah, HIV when we are fresh. Look at corona, herpes, because we notice it's tested a lot. We finish with the hepatitis. Yeah. Mycology, we'll just do an overview, then malaria. After that, tomorrow we'll be just looking at questions. So we can take a break up to 8:25. 8:25, we are starting on HIV. Hi, welcome back. Welcome back to this another session. Hope kunywa maji. We can now continue. Yeah, so HIV. HIV. HIV, number one, HIV is unique in terms of HIV doesn't follow that typical process that we've explained of at the RNA enters, its proteins are synthesized, and then that's the end of the story. HIV stands out, right? And to look at HIV, the best way to look at HIV is usually with the drugs, because the drugs of HIV, by knowing the HIV drugs, or rather just their classifications, you can know the replication cycle of HIV. When you know the drugs, you can know the cycle, right? And it's so that even when we get there, when we're looking at pharmacology of HIV, so that it's easier, let us work with the drugs. Let us work with the drugs so that we can integrate these two things, because they are intimately related. Because right now the current or the recommended first-line regimen for adults with HIV, it's the tenofovir, lamivudine, and dolutegravir. Tenofovir, lamivudine, and dolutegravir. Now, for the tenofovir and the lamivudine, we call them the nucleoside or nucleotide reverse transcriptase inhibitors, NRTIs. Right? In short, you just reverse transcriptase inhibitors, right? Meaning they inhibit that reverse transcriptase. And then looking at the other one, dolutegravir. Dolutegravir, we classify it as a integrase inhibitor, right? And then if someone's HIV is resistant to some of these drugs, and they can be given these other drugs called protease inhibitors, like so, atazanavir, lopinavir, such things. And at that point, the protease inhibitors, that tells us there's a protease enzyme somewhere doing something. So let us look at the life cycle of HIV, and while looking at the drugs, we won't even cover their mechanisms, their whole side effects, all of these things. We'll just look at them in terms of why are these drugs given? Why are these drugs given? Yes. Okay, so while it's loaded, let's start with what we know about HIV. HIV, or rather, not even what we know about HIV, what we know about the life cycle of a virus. The first thing HIV will do, it will attach somewhere, attach to a receptor somewhere. That's the first thing it needs to do. And we know the target of HIV is usually our CD4, right? So it will look for CD4 somewhere and attach to a specific receptor in the or on the cell membrane of the CD4. Once it does that, it's able to penetrate inside our CD4 cell. Once it penetrates inside our CD4 cell, it will release its genetic material. Which genetic material is this? In the case for HIV, HIV is an RNA. virus, right? In short, what it has is RNA. What it has is RNA. So it's RNA that it will release inside the cell. But it's unique in terms of, we call it a retrovirus, right? Retrovirus. Right? We even call the acronym is RVD. Someone has RVD, as retroviral disease, because it's HIV. This is where HIV becomes unique as compared to other other the other other viruses. What HIV will do, it will, using its RNA, or rather working on its RNA, it will synthesize what? It will synthesize a DNA. That's why we call it a retrovirus. It goes backward, right? It disobeys our central dogma that it should be DNA to RNA to protein. That RNA, what does it do? It's acted upon by the enzyme. This enzyme, HIV has this enzyme. It comes having this enzyme, this reverse transcriptase, right? To a what? To a DNA. Converts it from an RNA to a DNA. Now, if we convert it from an RNA to a DNA, the next thing we need to do, or rather now, at the end of the day, we know we need, for this HIV to make its proteins, we'll need, at the end of the day, we'll have to make an RNA somewhere, right? We'll have to make an RNA somewhere. And this is where the integrase enzyme comes through. Integrase enzyme, you know, from the name integration, right? That DNA that has been made from the RNA, it's moved to the nucleus. And when it's moved to the nucleus, there's this integrase enzyme. What does the integrase enzyme do? The integrase enzyme integrates that HIV DNA. It integrates that HIV DNA into our own DNA. It integrates that HIV DNA here into our own DNA. And then, now that integration has happened, after that, it's as simple as now what we just covered in in molecular genetics. Now the DNA has been integrated into our own DNA as our own RNA polymerase synthesizes what? It synthesizes RNA from our DNA. But part of that RNA is what? Part of that RNA is this HIV RNA. So we'll be making HIV proteins, right? We'll be making HIV proteins. But these proteins, they are kind of, not even kind of, these proteins, they are not active. They are not active proteins. They need another enzyme. This enzyme now we call the protease enzyme. What does the protease enzyme do? It cleaves this protein that has been made. It cleaves it to become, so that the proteins that have been made, they can become active. That is why we give protease inhibitors, because if we inhibit that protease enzyme, it means we've done what? HIV will hijack the mechanism. Yeah, it has hijacked, but we will have the last laugh. It will be like, hey, you hijacked the mechanism, but you didn't know hapo mwisho, there's nowhere you are going, right? There's nowhere you are going. I don't have a diagram that has really simplified this, and I'm not finding one. If someone has one, you can even send it to the group or display. Yeah. So let's just go back to the book. So here we've mentioned HIV contains what? RNA. RNA, it's reverse transcribed into DNA. DNA is done what? It's integrated into our own DNA. That is the host DNA, our own DNA. Then this is our own RNA polymerase. It has synthesized now the messenger RNA. This messenger RNA will be translated and we are able to make these viral proteins, polyproteins. But these viral proteins, they are not what? They are not active. They are not active with, especially this one. It's a polyprotein, meaning multiple proteins have been attached together. So if multiple proteins have been attached together, it means we need to break down that proteins to release the proteins. That is where this protease comes through. Protease, it cleaves the polyproteins into their now active components, which now will assemble into the mature virion. Then it's able to be released. It buds out and it goes and it infects another cell. So essentially, HIV is an RNA virus. Okay, it's an RNA virus. It belongs to this lentivirus family, but just know it's an RNA virus, right? First thing it will do, like any other virus, first of all, it needs to attach. It attaches to your cell, specifically to your CD4. It is to your CD4. Once it attaches there, it's able to gain entry into your cell. Gains entry, it releases its RNA. That RNA is acted on by the reverse transcriptase to make DNA. DNA is integrated into what? Into our own normal DNA. And once it has been integrated into our normal DNA, we will transcribe that DNA and we'll find ourselves making what? HIV proteins. These HIV proteins will release new HIV particles, which will go and infect other naive CD4 cells or other cells. Now, just to remind you what we mentioned yesterday regarding TB. TB, we said once TB enters your body, TB is, we said it's transmitted through respiratory air droplets, right? So we said once TB enters your body, what does it do? It will go to the lungs, right? You've inhaled it. Someone has coughed somewhere, you've inhaled TB. Goes to the lungs. It meets our first line defense, our alveolar macrophages. Once it meets our alveolar macrophages, once it
Leting
meets our
bwana,
alveolar
Leting itabidi umemute.
Kai, poleni.
once it meets our alveolar macrophages,
It is all right. It is all right.
The macrophage will phagocytose it. It will engulf it, but it can't kill it. So it calls for help, and help comes in form of CD4. And once they notice that this TB can't be killed, what do? They surround it. Remember, we said TB is a prisoner inside a healthy person, right? Surrounded by all of these immune cells, right? And these immune cells, they are what? Upregulated, or they are supported by these CD4 cells. That is how a healthy person contains TB. But HIV has come, it has infected our CD4 cell. Our CD4 cell is not able to accomplish its function. Our CD4 count goes low because they are dying. Then the TB, the guards of this prison, they are no longer there. They are no longer there. That's it. That's how TB becomes active. And HIV, in terms of transmission here, well, no, sexual contact, transfusion, contaminated needles, even perinatal transfusion is possible. That is why we need to test the mother, yeah, and all of this thing. But at least now there is that prevention of these things. Then directly we'll move to coronavirus as a whole. We won't look at it at COVID-19 specifically, just coronavirus as a unless someone has anything to add on COVID-19, HIV, or has any questions. Nancy, Saru.
No questions on my side.
Okay. So coronavirus, maybe we'll just summarizes. Coronaviruses, they are large, they are enveloped, and they are RNA viruses. I think I sang that when we were looking at that one-step growth curve. They are large, they are enveloped, they are RNA viruses, and they have spikes. Hence the name corona, which means crown. It gives us that appearance of a crown. So they are RNA viruses. So in terms of its, and they are positive stranded RNA viruses. So in terms of its replication, I think that one you can all say by now, it will positive stranded, it is equal to one messenger RNA. A messenger RNA will be translated to the proteins. The RNA will be replicated and voila. Right? Yeah. And now specifically for COVID-19, what was, or rather the vaccine, what are the vaccine we cover it tomorrow, or not tomorrow, next week, because now that we'll have to go deep into the pathophysiology. So that one will cover it tomorrow. But just know that COVID-19 or coronaviruses as a whole, they are single-stranded RNA viruses. Positive single-stranded RNA viruses. It's one of the larger viruses we have, and they are enveloped. Yeah, envelope, don't forget enveloped. Why were we using sanitizer? Sanitizer destroys that envelope. And we said what? If the envelope is compromised, that's the end of the virus. If the envelope is compromised, that's the end of the virus. Yeah, so next we'll just go to hepatitis. So for hepatitis, number one, we've already said hepatitis we know hepatitis runs from A to E. Hepatitis A, hepatitis B, hepatitis runs from A to E. And one thing we've appreciated is that hepatitis B is the only DNA virus, or the only DNA containing virus among the hepatitis. All the others, A, C, D, and E, they are RNA viruses. But Hep B, it's a DNA virus. And which ones can cause chronic hepatitis and which one can cause acute hepatitis? For that, we have, for chronic hepatitis, just Hep B and Hep C. Hep B and Hep C. the other one, the hep E, is called acute hepatitis. It just causes acute hepatitis. So A and E, acute hepatitis. B and C, chronic hepatitis. Now you'll notice there is one specific one we are leaving out, and that is what? Hep D, hepatitis D virus. So we've said A and E, acute, B and C, chronic. So what does D causes? What does hepatitis D cause? Now, hepatitis D, number one, it's classified or it's regarded to as an immature virus or an incomplete virus, right? Your hepatitis D cannot infect you while on its own. It's incapable of that. Hepatitis D cannot infect you while on its own. Hepatitis D needs hepatitis B for it to, for us, even for it to infect a cell. Hepatitis D, dog, it needs the presence of hepatitis B to infect you. So that's a question that just can be asked. Which one of all is an incomplete virus, or which virus needs another virus to do what? To infect you. That is Hep D. Why? Because it needs that envelope from Hep B. There's a specific Hep B supplies to it that it usually does not have. Hence, why we are saying Hep D is an incomplete virus or an immature virus, because it can't infect you while on its own. It needs this Hep D to be present. Just want to highlight the exact need. Is it a coating that it needs? It is. Hepatitis D infection is unique because it can only occur in people who are also infected with hepatitis B, right? It needs that Hep B to be present for it to infect you. Then here we say that yeah, it's a defective virus in that it requires that Hep B for viral replication, right? It requires Hep B for viral replication because this it needs that coating. Yeah. In short, Hep D is an incomplete virus. Hep D is an immature virus that needs Hep B to be there to infect you. However, Hep D is still an RNA virus. Okay. So in short, Hep B and Hep D, those ones, they go together, right? Those ones, they go together. Now, let us look at Hep B. Number one, we've said what is a DNA virus, right? It's a DNA virus. And for hepatitis, remember, how do we differentiate between acute and chronic hepatitis? Acute hepatitis, less than 6 months. Someone is presenting with these symptoms of a liver disease for less than 6 months. Chronic hepatitis, after it has surpassed that 6-month line, we're able to say, hey, this person is now having chronic hepatitis, and they need to be treated accordingly. So it is, it's a double-stranded enveloped DNA virus. Double-stranded enveloped DNA virus, right? And we know someone has a liver disease, or if someone is having liver issues, we can already guess the symptoms. Kina jaundice. So jaundice, pale stools, dark urine, right? Nausea, because of that buildup of bilirubin. And then once we test your blood, we will see elevated level of ALT, AST, such things. So let's look at the mode of transmission. Number one, Hep B, injections. Injections here, or in this day and age, these injections here, when you see injections, we are looking at these people who are number one, self-inject drugs, right? Likes of kina heroin. these people who self-inject and they share these needles, right? But also healthcare workers are also at risk because you can inject someone, then through these pricks, you can also infect yourself, right? So injection is one key transmission method of hepatitis B. The other mode of transmission is sexual intercourse. Through sexual intercourse, one can transmit hepatitis from the partner can transmit hepatitis to their partner, both in heterosexual and in homosexual men, but it being homosexual men having a higher risk of infection than the heterosexual, right? So even for the mother's milk also is a source of infection. Blood transfusion, things such as hepatitis is things that we test for before blood transfusion. So majorly injections and sexual transmission. We're going to look at it that is, in terms of replication, it's what we've seen. It's the general replication over the general replication of the DNA virus. However, with one little twist. Remember, and that one little twist, you can be able to guess that twist by the drugs we use to treat Hep B. Hep B, we use the same tenofovir and lamivudine, right? And that will tell you that there is some reverse transcriptase also here. I mean, to treat a disease that is not HIV, if we are not inhibiting reverse transcriptase, right? So this is the replication cycle of hepatitis B. Number one, we said there's entry of the virus inside your cell. It releases that DNA material. The DNA will move to your nucleus. Once it moves to your nucleus, it will be transcribed. We know our RNA polymerase is where? In the nucleus, right? So that it will be transcribed by our own RNA polymerase to produce some messenger RNAs. Now, these messenger RNAs, they are what serve as they'll serve as a template both for DNA synthesis and some for proteins. Now, this is where reverse transcriptase comes in. Reverse transcriptase, it takes one of the RNAs and synthesizes what? It synthesizes a complementary DNA strand, right? It synthesizes a complementary DNA strand. In short, what you need to understand is hepatitis B is a what? It's a DNA virus. That means when it gets inside your cell, it broke down into its constituents. But when it leaves your cell, it needs to be a DNA virus still, right? So once it got inside your cell and it entered into your nucleus, we changed that, we used that DNA material to make RNA. At the very end of the day, for this cell to release hepatitis B, we have again to make a DNA for it to exit, for it to say now that virion is complete. And this is where reverse transcriptase comes in. It acts on one of the RNAs that has been made to make a complementary DNA strand. This complementary DNA strand is what will be added to the new virus and will leave the cell. So if you ask which two viruses have this reverse transcriptase, it's the HIV and the hepatitis B virus. So the symptoms of a liver disease, in jaundice, all of these things we've seen. Then more the clinical stuff, we'll see it more when we are doing the clinical stuff. So can the other ones we've said they are what? They are RNA viruses. So if Nini, we can move to Nini, we can move to what? We can move to now the herpes viridae, which will help us revise the replication of DNA viruses. Like a typical DNA virus, because Hep B is unique in that it has its own, it has the reverse transcriptase enzyme. So the Herpes viridae family, yeah, it's a big family from the alpha Herpes viridae, beta to gamma Herpes viridae. Now for the alpha, we have the herpes simplex 1, herpes simplex 2, and the varicella zoster. Herpes simplex 1 usually is the one that causes the cold sores, right? Herpes simplex 2, the one that causes the genital sores. Then the varicella zoster virus is the causative agent of chickenpox, right? So chickenpox is a viral infection. Chickenpox is just a viral infection, right? Then you notice from that name, varicella zoster virus. That this one we call it herpes zoster, right? Herpes zoster or shingles. Shingles, the other name. And that is just chickenpox that has returned. And it usually, there's a way it appears, half your body, because we will see this herpes viridae family. They are notorious for hiding or going to your nerve. That is where they go to relax. They go to your nerves, they go and relax there. So once they are reactivated, they affect the specific region that nerve serves. Yeah. So for herpes simplex 1 and 2, we already said. So we say number one, they are DNA viruses, right? And they are enveloped, right? They are enveloped DNA viruses. We've seen the major classifications, alpha, beta, and gamma. Alpha, we've seen, is the typical HSV1 and 2 and varicella zoster. Beta, majorly we have the cytomegalovirus. And in gamma, we have the EBV. We know for the EBV, we know for it being having a carcinogenic component, can be implicated in some of these cancers. For the cytomegalovirus, we see cytomegalovirus with AIDS patients again, it affecting the eyes and all such things. Yeah. So with this, again, happens that ability after that active disease, they go and relax somewhere in the neurons. They go and relax somewhere in the neurons here. Time you got chickenpox, here you are. How is it? Yeah, this is the first time you got chickenpox was all over, right? It was all over here. Then when you got better, what did the chickenpox virus do? It your nerves, and specifically there to your ganglion or to your dermatosome, whatever you want to call it. It went there and it became latent. Latent means it just went and relaxed somewhere here in the nerve, right? So when it was reactivated, maybe you got immunocompromised, yeah, you started taking steroids, maybe in a stressful situation, when we'll move from this place that it was and just follow the nerves. That is why you will see with the shingles, the zoster, you'll see it affecting half the knee. Because we know from the spinal cord, a nerve will, or rather, a nerve will just go into one half. It doesn't go to both sides. That can help. Let's see, I'm not finding it. It just goes to half your body. And most come, there's a rash just on one half. There are a number of rashes just on one half of their body. That really raises the suspicion. Yeah, yeah, just even now, just Google shingles or herpes. So you'll notice that it just covers one half of the body to one side, right? Just one half of the body. And this is because it establishes latency, or it goes and sleeps here in the nerves. In terms of the diseases causes, it already says HSV1, the cold sores, HSV2, the genital sores, but either can cause the other. HSV2 can still cause cold sores. HSV1 can still cause genital disease, but it's not common, right? Treatment is the same, acyclovir. For the prevention, or rather, no, not for the prevention, for the transmission, we are looking at sexual intercourse, right? Because it's genital, we are seeing genital source, so sexual intercourse. And also, if a person is having the cold sores and you're having an open skin, right, or a break in your skin, there's also that 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 mode of transmission can occur. Even the perinatal transmission can occur, and that is so dangerous because in children we will see it can cause the likes of encephalitis, right? This is why you always need to screen the mother for all of this number of diseases. We will say the likes of rubella, because heart disease in the newborn, right? All of these things. Yeah. Mm. So for herpes viride, I think give that is it. If you see, if someone has something to add now, this is the time. This is why it's read this herpes viride, all of these topics, because now we'd be adding to what we've said and emphasizing all of these things. But so lastly, we take a 10-minute break at 9:20. We look at malaria, and then that will be it. Okay. Welcome back. Hope you feel refreshed.
Wait.
So malaria. So malaria, we know it's transmitted by mosquitoes. You know, malaria is nothing new since primary school. Transmitted by the female Anopheles mosquitoes, right? The symptoms, you know, the fever, the chills, the headache, there may be some diarrhea, there may be some vomiting. Treatment, we've heard about the AL, Artemether plus lumefantrine, all of these things, right? So briefly, or in many words, because it's the most significant part of malaria. So pathophysiology. How does malaria see, right? Or rather, how do you get malaria? Let's start there. How do you get malaria? So, first of all, we know the story starts with mosquito, right? That number one, there's a mosquito that has malaria, right? There's a mosquito that has malaria. So when it's feeding, on you, well, it wants to take blood from you. It deposits this stuff called sporozoites. Now, these phases of malaria are very important. So just find a way to memorize it. That the mosquito injects or deposits sporozoites. The sporozoites are in it. You can see saliva, right? So the mosquito will deposit its sporozoites while it's feeding on your blood. Now those sporozoites, they enter the bloodstream and they travel to the liver. In the liver, they mature into stuff called merozoites. Now, they mature. So sporozoites enter your blood and they go to the liver. In the liver, that is where they mature. They mature to form this stuff. Now we call them merozoites, right? Merozoites. Now, the merozoites are the stuff that will now go to your, or rather, it's the one that will attack your red blood cells. The one that will attack your red blood cells. It enters into your red blood cell, and once it enters into your red blood cell, the merozoites, now we call it a trophozoite. Now, the trophozoite is the one that will multiply inside your red blood cell. It will multiply, producing new merozoites. These merozoites will be released when the red blood cell ruptures. And when it ruptures, it releases these merozoites, which will enter again into other RBCs, be converted to trophozoites. Trophozoites will multiply, producing new merozoites. The RBC will rupture, and again, it's a cycle. But then, some of these merozoites, they become gametocytes. The male gametocyte and the female gametocyte. And now, this gametocyte, now it's not infected. So that's something you also need to know. You need to know that even you can have mosquito malaria, right? That mosquito malaria. It's not a one-sided thing. Humans can give mosquito malaria, because for a human who is infected with malaria, then a female Anopheles mosquito comes to bite this human. But this Anopheles mosquito is not infected with malaria. And then while it's taking its meal on you, while it's feasting on you, it will feast on some of these gametocytes. Once this happens, then the mosquito is now even able to get malaria, or it absorbs malaria from you. Now that's the summary version. So what mosquito, right? But what mosquito, an infected mosquito will take from you is what? The gametocytes, right? The sporozoids will go to the liver, release merozoites. The merozoids will infect the RBC. The RBC, once in the RBC, the merozoids will become trophozoites. They'll multiply into more merozoids. Yeah, the process continues. Some of the merozoids transformed into gametocyte, and the female mosquito takes them. Now let's look at a bit more detailed one. But I'm assuming the general cycle you've got. Now we'll look at a more detailed one in our here, because these phases are sometimes, yeah. So here we are seeing two phases. There's this pre-erythrocytic schizogony or schizogony, whatever you want to call it. And there's the erythrocytic schizogony or schizogony, right? There's a pre-erythrocytic schizogony and then the erythroschizogony. So erythrocytes are RBCs. So we can even by the name we can see the pre-erythrocytic. This is before it has gotten to the RBC. Then the erythrocytic is now when the cycle is here in the red blood cells, in the RBCs. So again, let's repeat. We know malaria, we know the Plasmodium falciparum, Plasmodium vivax, Plasmodium ovale, Plasmodium malariae, right? We know all of these species, right? And falciparum it's the worst. It's the one that causes the serious malaria, complicated malaria. So this here, mosquito, here it is, the sporozoids have entered your bloodstream. We said, where do they run to? They run to the liver, right? This is the pre-erythrocytic, because we've not yet found the RBC. The pre-erythrocytic, the sporozoid, it matures, leave alone the hypnozoids for now. We'll look at hypnozoids on their own first. The sporozoids we are seeing here, it matures, it grows into a trophozoid in a pre-erythrocytic schizoid, and then what forms the hepatic merozoids, right? Now the hepatic merozoids are what is released. It's simply what the other book told us. Sporozoids enter the liver, merozoids are released from the liver, just that this one has looked at the growth phase. Now the merozoids, we said, what do? The merozoids, they infected the red blood cell, right? They entered into the red blood cell. Once they entered inside the red blood cell, from this ring form, we see now the late trophozoids, or now we said once the merozoid enters the RBC, we form a trophozoid. Now the trophozoid is what multiplies, and then once it multiplies, we have here the mature schizon. In the mature schizon, there'll be lysis of this RBC, and the RBC will release what? An erythrocytic merozoid. Remember the other one's the hepatic, because it's released from the liver. Now we have an erythrocytic merozoid. This erythrocytic merozoid, what can it do? It can go infect other RBCs, but we said some can be converted to gametocyte, the male gametocyte and the female gametocyte, the male gametocytes and the female gametocyte. And we are seeing here, the gametocytes are transmitted by you. That's when the gametocytes are transmitted to the mosquito. Both the male and the female. They go into and they mature into sporozoids. Now these sporozoites are what again will be injected into you. So essentially, it's what the other book has said. This one has mostly introduced the concept of erythrocytic schizogony and the erythrocyte. 4 major types. I think it was revised to 5. Not remembering the name of the 5th one. It is even. No, it's not. 1, 2, 3, 4. Okay, there's a 5th one. Okay, but there are 4 traditional major types. We have the Plasmodium falciparum, Plasmodium vivax, Plasmodium ovale, and Plasmodium malariae. Right? Plasmodium falciparum, we know this is the toughest. This is the toughest of the Plasmodium. Then malaria is the weakest, right? Then there are these 2, Plasmodium vivax and Plasmodium ovale. Plasmodium vivax and ovale, they have the unique ability that once the sporozoites enter into the liver, some will develop into the merozoites, infect RBCs, and the process continues, but some will enter into a latent phase called hypnozoites, right? They enter into a latent phase. In short, it's like they go into hiding. They enter the liver and they find a good place to hide. They go and hide there. Once they hide, you go, you say, oh, I'm sick. We test you. We find it's malaria. We treat you. And then we send you home. But then after a few weeks, come back again. They grew, or rather they were activated, and they again became the sporozoites again. Now that to the merozoites, to the RBCs, and all of that again. So these 2, Plasmodium vivax and Plasmodium ovale, we say they can establish a latent infection in the liver. They can establish a latent infection in the liver. Remember what we said about that infection, right? That term infection. That if someone is displaying the active disease, no, we said that infection is we said infection is you being exposed to that particular organism. That's what we said infection is. So once we say they have established a latent infection, we are saying that it's a dormant infection, meaning it's just there. It's just there chilling, right? And it's the same with TB, within TB, and also the same with what we just looked at, the chicken pox. It goes and establishes a latent infection where somewhere in your nerves, somewhere in your ganglion, a latent infection, meaning you still have, like, if you've ever been infected, if you've ever had chicken pox, the disease is chicken pox, you are even now, that's that varicella zoster virus. Why? Because that virus is still in you. It's still somewhere in your nerves, still somewhere in your neurons, in your ganglia, just there chilling, right? Yeah. So this one's, it's the same. Now this one that they established the latent infection in the liver. Then the relapse can happen, and then the active disease occurs. So yeah, that's malaria. That's malaria. Less I know for malaria, Nani has a lot to add. Maybe maybe she can add Sanaipei. No addition on malaria. You guys now, you're just keeping quiet. Yeah. Well, malaria, you can't really can't lack something to add. Mhm. Okay, okay. And we'll go to Nini. Just an overview of my courses, then we close. But hey, be active, Nini. Otherwise, the discussions will just die off. If it's just this side, yeah, I'll tell you like from my perspective, from this side, it's like I'm just talking to myself. If these people are not contributing, Nini, it ends up not being a discussion. It comes as if it's a teaching session. I will move to my courses. So fungi. The short topic. Fungi, number one, something unique. They are eukaryotes. What other eukaryotes do we know? Humans, right? Like the likes of bacteria, which are prokaryotes. Fungi are eukaryotes. In the very fact that they are eukaryotes, that makes them a little hard to viral infection. Typical days of treatment for an infection is just 5 days. Is antiviral infections minimum usually been 7 days. Most regimens are preferring 2 weeks of treatment. For things even like nail infection or onychomycosis, that one can even go for months, depending on the location. So fungi, they are not easy to treat. Number one, because they are eukaryotes. Why is this significant? Is because remember the concept of the magic bullet, that once you're given a drug, you're given this drug to treat the disease, to treat the patient, right? But magic bullet is in terms of if a patient is taking this amoxicillin, if a patient is taking this metronidazole, this doxycycline, whatever antibiotic it is, you want this antibiotic to somehow not affect this person's cell, but just go and harm that bacterial cell. And that's why we call them magic bullets. Because somehow they do not harm you, but they harm this. They target this specific bacteria that is inside of you, you know? So that's hence the name magic. That's magic, right? So with eukaryotes, it's particularly hard to do what? To have magic bullets. Because we are eukaryotes and they are eukaryotes. So we notice that the mechanisms are different. The mechanisms are more or less similar, right? So that makes it a little harder to treat as compared to the other ones, such as bacteria, such as, yeah. So primarily on the location where they cause the infection. We can see here that for the cutaneous, for the skin diseases, mostly we have this Trichophyton, Microsporum, and Epidermophyton species. This EMT, as EMT, Epiderm, Microsporum, and Trichophyton. These three, they're the ones notorious for causing all of these tinea capitis, tinea what, tinea corporis, tinea cruris, all of these teneas, you know, those teneas, once we say tinea corporis, tinea cruris, they sound as if they are the actual organisms. They are not the organisms, they are not named tinea corporis, tinea cruris, tinea what. Those tinea is just a name of, it's the name of the disease. You can say for tinea pedis, that is of the foot. You can see it's this Trichophyton, Epidermophyton, Trichophyton. Tinea capitis, again, Trichophyton, Microsporum. Yeah. So it's this is the most common. If someone asks you the most common fungi is this Epidermophyton, Microsporum, and Trichophyton species. Because even when we are attached to the community, how many people came with niko na kashilingi, o mtoto wangu alienda shule nywele imejaa, white stuff, all of these things, right? Even the topical Clinaclozol B, right? These are one of the most selling creams because fungal infections are common. I mean, people also use it for bleaching, but business versus ethics. I don't know how you feel about that. Anyway, now those are the cutaneous infective agents. Then the other class, the other important class are these systemic agents. And most of these are respiratory lung disease, the likes of Histoplasma capsulatum, coccidioides, immitis, blastomyces, dermatitis, all of these things. Mostly they cause respiratory disease. Mostly they cause that respiratory disease. And the other thing I forgot to mention is that fungal infections, typically they are diseases of, especially for this systemic, not the topical ones happen to anyone. These systemic ones, individuals. So we'll see HIV patients, neutropenic patients, corticosteroid patients. Yeah, fungal infections, the systemic ones, not the topical. Topical, it happens. Today, if you are a teacher in a school, and you know these kids are the ones who mostly have fungal infections, and you interacted with them, in 2 weeks' time, you will see you've started developing a But these systemic and the opportunistic pathogens. The opportunistic pathogens, I know, Candida albicans, that one we know it. Cryptococcus neoformans, it's notorious for causing cryptococcal meningitis in HIV patients, right? Aspergillus fumigatus, same HIV patients, just respiratory lung disease. Pneumocystis jirovecii, right? PCP, right? PCP, we know HIV patients, we always giving them what? Cotrimoxazole. Why do we give them cotrimoxazole? To prevent opportunistic infections in this PCP or PJP. Pneumocystis jirovecii pneumoniae. Yeah. So, looking at the structure of fungi, is that the fungal cell wall, in the bacterial cell wall, we notice that it's more of a peptidoglycan layer. Major of this N-acetylglucosamine. It's a polymer of N-acetylglucosamine. Why is this name familiar? Because in the peptidoglycan layer, we said it's an alternating sequence of N-acetylglucosamine and N-acetylmuramic acid. NAG-NAM, NAG-NAM, NAG-NAM. What links the two are an amino acid, a short amino acid chain, or a short peptide. And that is why there's these drugs, penicillins. Where do they work on that? The enzyme that enables this link in the transpeptidase, right? Yeah. So then something unique and something that is most of these drugs you will see they utilize is that the fungal cell membrane, the plasma membrane or cell membrane, it contains agosterol. That is the unique thing. That is where our bullet, you'll see most of our magic bullets hit the agosterol, right? Because in our cell and in membrane, us we have cholesterol, but them they have agosterol. So that tells us if we want to make a magic bullet, this agosterol will be the stuff to target. And that is where most drugs work, these common drugs that we use, like clotrimazole, fluconazole, itraconazole, ketoconazole, those are zole antifungals. Then amphotericin B, it does bind to that agosterol component. Looking at terbinafine. Terbinafine is another common antifungal. It inhibits synthesis of that agosterol. So agosterol is really a vital component that is in the fungi that even us as pharmacists we target. So if you're looking to develop a drug, this agosterol is where you'd be. You'd play fungus. They do not. Or rather they exist in two forms, right? There's the yeast and there's the mold, right? There's the yeast and there's the mold. Now, yesterday we saw something that also exists in the same form. We call it pleomorphic, which the bacteria was Haemophilus influenza. Remember us saying Haemophilus influenza is pleomorphic, right? It ranges from a rod to a long, slender filament. Even call it what? A cocobacilli. A cocobacilli. Coco, we know means spherical shape. Bacilli, rod shaped, right? So just but when it comes to fungus, we see it's just two forms. It can be a mold or a yeast. A mold or a yeast. However, some they can switch between being a mold and they become a yeast. Now the mold is filamentous. You can just remember it's filamentous. So here you see hyphal filaments, right? Hyphal filaments or hyphae, right? Those are the terms that will be used. But for the yeast, Yes, they're just some cells which are, it's just cells, right? Generally just cells. But the mold is where you see the hyphae. That term hyphae, you see it being used. Yeah, filaments, or all of these terms will be used there, right? So regarding all of these types of mycosis, that one we'll see it again. We're discussing these diseases caused by diseases caused by this microorganism, like cryptococcal meningitis and all of this. But just before or something to interest is that this in systemic plasma, coccidioides blast, their pathophysiology is TB. They will enter the most common route of infection will be through the inhalation, and they will enter, and your cells will try to contain them first. Once that fails, that is what leads to the infection. And that's why we see these systemic fungal infection mostly. Yeah, that's it from me. And for microbiology, the other topics, just go through them. If you have any questions, send them to the group. And yeah, me, I'm done. Unless someone has something to add, that's it from me.